Hi, I'm Curtis Berlinguette. I'm a professor of chemistry and chemical engineering at the University of British Columbia. And it's a real privilege to be able to share with you today some of our research that is ongoing here in Vancouver, Canada. Our group's interests today span a number of different areas, ranging from self-driving labs to cold fusion to membrane reactors, a technology that lets you hydrogenate organic compounds without ever using H2 gas, to smart windows. But our presentation today is really going to be focused around utilizing CO2 and thinking about it in terms of the entire value chain. And this is what's actually led us to this focus on reducing bicarbonate solutions in electrochemical reactors. And this will become hopefully quite clear on why we're doing that as we work through this presentation. As we think about how we are going to reduce our CO2 emissions and CO2 that's already been emitted, this will ultimately rely on CO2 capture technologies. And so once you have that captured CO2, what do you do with it? And this is where we fit in this value chain. Our group is interested in designing electrolyzers that are capable of using electricity to convert that captured CO2 into chemicals and fuels that can then be sold and actually have monetary value. As we design these electrolyzers, it's useful to look at industrial systems that already use electrolyzers. And this includes a chlor-alkali process or hydrogen generation. And when you look at all of these systems, they're all characterized by these features. They have high reaction rates, so they need to operate at current densities of greater than 200 milliamps per square centimeter. They need to operate with a high energy efficiency, and this means that the voltages of a CO2 electrolyzer must be below 3 volts. Anything higher than that is unlikely to make sense. They must have a high product selectivity. That means that you need to be forming a single product at the other end, otherwise it's going to get quite expensive to separate a range of different products. You need to have a high CO2 utilization rate, and that means getting those rates beyond the 20% where they're currently at for many of the state-of-the-art CO2 electrolyzers today. And then finally, we need to have a system that is robust and stable and can last for several years before actually being broken down and replenished. And so those are the big 5 metrics that you need to hit if you want to be able to commercialize one of these CO2 electrolyzers. And I can tell you that today there are no commercial CO2 electrolyzers that exist. Okay, there's no system that has been able to check off all of those boxes. And so that's really why we and many others are continuing to look at different ways we can design these electrochemical reactors to hit those metrics. If we do look at the state-of-the-art CO2 electrolyzers that are out there today, they tend to be characterized by the use of a gaseous CO2 feedstock. If you try to feed your electrolyzer with an aqueous liquid medium, you're going to be constrained by the amount of CO2 that you can dissolve into that medium. And because of that low solubility of CO2 in water, you end up starving your electrode. And so the way to get around this is that you just bypass the use of an aqueous medium, and you then feed that electrolyzer with a gaseous feedstock. And this plot, I think, shows very simply how the differences of moving from a liquid to a gas phase can be really quite significant. This is a flow cell where really the only thing that's been changed here is the phase of that feedstock. And you can see that the Faradaic efficiencies at a range of current densities are over double that of the liquid feedstock. Okay, so this really points to using a gaseous CO2 feedstock is going to give you the high current densities that you really need to be operating at. And so by extension of this, if you're going to work with a gaseous feedstock, it makes sense to then pump that electrolyzer with more and more CO2. And indeed, if you actually start to operate your electrolyzer under pressure, under pressurized CO2, now you can start to see the system operating at really substantial current densities. And this has been demonstrated by us and others, and how you can now start to get to current densities are well north of 200 milliamps per square centimeter. Okay, so working with gaseous phase CO2 feedstock seems to make sense, but we really need to think about the entire value chain of converting CO2, captured CO2, all the way to the final product. Okay, and so that's what this schematic is meant to indicate. All right, so on the left-hand side, we've got our CO2 source, and this could be a flue stack or atmospheric CO2. And what happens is that you need to have some absorber step. So you have some absorbent that will react, in most cases, spontaneously with that CO2 to capture that CO2. Now you're left with this CO2-rich absorbent after it's been caught in this absorber. So now you've got the CO2 captured, but you need to release that CO2. So that way you can actually pump a pure stream of CO2 in your electrolyzer. And this is a step that, in the way that it's currently done, in most cases, is very energy intensive, trying to get that CO2 away from that CO2-rich absorbent. In many cases, people just use heat to be able to do that. And once you do that, then you regenerate your CO2 lean sorbent that can then go back and react with their incoming CO2 from the atmosphere fluid stack. And now you're closing the loop there, and now you're releasing CO2 in its pure form. Now you've got the CO2, but as I said before, if you want your electrolyzer to be operating at high current densities, you almost certainly need to pressurize that CO2. So now you need to add a compression step. And so there's an energy penalty associated with that. There's additional CapEx associated with that. And now you've got your pressurized CO2, and you can finally bring it into the CO2 electrolyzer. Now your electrolyzer is also going to consume energy, and by its very definition, you're using electricity to drive some chemical transformation. Now, in your electrolyzer, in a CO2 electrolyzer, when you're pumping it with CO2 gas, you then have to consider the fact that you've got low CO2 utilization rates. And so that means that the majority of the CO2 that's going into your CO2 electrolyzer passes right through without ever reacting. Okay, so that's one of the challenges. So you end up actually converting a relatively small amount of the incoming CO2 that you captured into some carbon-based products. So that is a major challenge. The other is the fact that the CO2 that's in your electrolyzer, it's going to be capable of reacting with hydroxide that will be generated through the CO2 reduction reaction. And so that is going to be a parasitic reaction to form bicarbonate and carbonates. And through that reaction, you're also losing a lot of your CO2 to undesirable products. Okay, and just to illustrate the importance of these two things as we look at the entire system of CO2 electrolysis, think about the amount of CO2 that's actually going into your cathode compartment. Again, we have these are currently characterized by relatively low CO2 utilization rates, less than 20%. In this case, we're going to approximate it to about 15%. Again, half of that ends up reacting with bicarbonate, reacting with hydroxide, which is a byproduct of the CO2 reduction reaction. So you're generating hydroxide, and that hydroxide can react with bicarbonate. And so you are now generating bicarbonate. You do have your CO2 products, but you can see that's a pretty small fraction of the CO2RR products that are made given the amount of CO2 that's gone into your system. And you've got some other problems that we need to address. You've got crossover across the membrane that separates the anode and cathode. And so in the end, you end up actually with a very small fraction of CO2RR products, and you have a lot of unreacted CO2. And this is a situation that is really, really challenging. And so this is why we started looking at alternative ways to address this. And this is why we're now working on bicarbonate electrolysis. Okay, so the top half of this slide is the same scheme that I showed you just moments ago. Again, we've got our CO2 source going through the absorber, the stripper, the compressor, into the CO2 electrolyzer, and then we've got 10 to 30% products. All right, that is what most of the community is working on. We asked the question, is there a way where we can actually take the CO2-rich absorbent that's generated upon reaction of the CO2, can we take that and then directly feed our electrolyzer with it? Can we do that? And so when we think about systems that use carbonate-rich solutions, these are solutions that contain hydroxide. You know, when that way actually reacts with CO2 to form bicarbonate-rich solutions. Okay, so you're starting with a carbonate-rich solutions going to a bicarbonate-rich solution. Can we actually just use this bicarbonate-rich solution and feed our electrolyzer with it to convert this carbon, that captured carbon, into useful products? And what I'll show you through this presentation is that the answer is yes. And the answer is yes, and there are a number of advantages to doing this. One is that, as I will show you later, the CO2 utilization rate is quite a bit higher with a bicarbonate electrolyzer than a CO2 electrolyzer, more than twofold higher. So that allows us to go after far more product than what you're dealing with a CO2 electrolyzer. The other advantages of this is that we're now dealing with an electrolyzer that relies on a liquid feedstock instead of a gaseous feedstock. And the engineering of a liquid-fed electrolyzer is, in my view, a lot easier to engineer, design, and run and maintain than a gas phase electrolyzer setup, where you have to always be managing a gaseous feedstock, dealing with seals, making sure that you don't have any ruptures. Liquid electrolyzers just seem to be a lot easier to design and operate. The other interesting thing is if you look at these two schemes, right, we've got our capture unit or absorber unit, stripper, compressor, and then the electrolyzer. You can see that with our scheme, we completely knock out the most energy intensive step and also the most capital intensive step through this process. We also knock out the need for capital intensive compressors and that additional energy penalty. All right, we just need the absorber and we just need the electrolyzer. So our electrolyzers should in principle be cheaper than our CO2 electrolyzers, and we've just knocked this out. So if we can make this work, this is really fundamentally different from an economic perspective on how we take CO2 all the way to the final product. As I said before, this bicarbonate electrolyzer does work. We've demonstrated this for the first time in the world a couple of years ago. But admittedly, the performance of our system, as we first reported, wasn't great, but it worked a lot better than anybody expected it to. Okay, so at that point in time, we were dealing with a system that at a couple hundred milliamps had a nearly 37% Faraday efficiency. It was operating at a high voltage, 3.4 volts. And again, that's at a low current density. So not even at high current densities. So we're not even remotely close to the state of the art of CO2 electrolyzers that are up here in the top right corner of this diagram. Okay, but nonetheless, we had a proof of principle experiment established here. And since then, I can tell you that our team has actually taken this and is now hitting performance metrics that are comparable or even better than many CO2 electrolyzers that are out there. So we're now operating at near unity Faradaic efficiencies at voltages approaching 2 volts. So we're pretty excited about this. And these are current densities that are at 500 milliamps per square centimeter. And so I'll walk you through how we got there over the last couple of years. Okay, so how do we actually convert CO2 into product using a bicarbonate electrolyzer? And this really all comes down to this connection between bicarbonate and CO2. Okay, so this is all acid-base chemistry. So if we actually have a source of protons, we can actually react that electrochemically inert bicarbonate species into CO2. Okay, so that's not an electrochemical step. That is an acid-base step. So as long as we have a proton available, we can now convert that into CO2. So you form that CO2, and it's the CO2 species that then gets electrochemically reduced into carbon monoxide or other products, depending on the catalyst that you use. Okay, and so this acid-base connection really does link CO2 capture with CO2 conversion. It's actually quite fun. Okay, and so just to demonstrate the opportunity that we have available with a bicarbonate electrolyzer, I'm going to show you this simple experiment right here. We simply have an H cell where we have an anode compartment on the left-hand side. We've got a cathode compartment on the right-hand side. And both of these compartments with aqueous media are then separated by a bipolar membrane that's situated between those two vessels. Okay, so we've got electrodes in each one of those compartments. We've got an anode and we've got a cathode. The anode is sitting at 1 molar KOH, so strong basic solution. The cathode is sitting at 3 molar bicarbonate. Now, what happens is that when we start passing current through our system, we started to see these bubbles appearing right at the membrane surface. Okay, and so we were super excited by this because these bubbles provided a clear indication that we were actually making CO2 right at the interface. And it's not just that we were making CO2, we were making so much CO2 right at the interface that it was forming bubbles. It was beyond the saturation limits of our aqueous solution. Okay, and so this is what we say is where the bicarbonate in a reaction chamber is reacting with protons that are supplied from the bipolar membrane. So the bipolar membrane in which the protons go to the right and hydroxide goes to the left. So that keeps the pH high in this particular scheme on the anode compartment. And we're providing this acidic environment right at the surface of that membrane in the cathode compartment. And so that reaction between the bicarbonate that is our electrolyte species plus protons coming from the membrane, that actually forms CO2 gas. And we refer to this as in situ generated CO2, ICO2. So anytime you see ICO2 in this presentation, what I mean by that is that it's CO2 that is actually generated within the reactor. It's not CO2 that is supplied from an external source going into the flow cell. Okay, so the fact that we form bubbles is exciting to us because that means we are generating a sufficiently high concentration of CO2 right at the membrane surface, and that's where a catalyst is ultimately going to be pressed up against. We're generating more CO2 right there than you could possibly get to with a liquid aqueous medium by pumping it with CO2 before it goes into the reactor. Okay, it would just be saturated and you would lose it. So the bubbles were a very big deal for us. We were excited about the bubbles. Okay, so based on the fact that we saw these bubbles, we went out and designed a flow cell to convert this in situ generated CO2 to useful products. And so for much of this presentation, this is really the design of the flow cells that we're using. We've got a flow cell. This is like a graphic up here on the right. So you've got this housing on each side, and that's just designed so that way we can keep everything contained and provide a supply of our feedstocks, both at the anode and the cathode. That is then containing these flow plates on either side, and as we'll show you in a couple of slides here, that the flow plate geometries can change depending on our needs. And then on the anode side, we're using a commercially available nickel mesh electrode that's pressed up against a commercial bipolar membrane that's pressed up against a commercially available silver catalyst layer. And then we also have a flow plate on this side. All right, so the chemistry in our reactor here is that we've got hydroxide in the anode generating oxygen on that side. On the cathode side, we've got two reactions that we need to consider. We've got bicarbonate plus protons giving us that in situ generated CO2. And then that in situ generated CO2 is actually what gets electrochemically reduced at that silver cathode to form, to generate CO. And we can change that silver to copper, for example, to make multi-carbon products. But we're just going to keep the talk confined to the generation of CO today. So once we had this proof of concept experiment established, then this really became more of an engineering problem, and we wanted to go through and optimize for all of these different components to try to get the best performance we possibly could out of a bicarbonate electrolyzer. Could we do a lot better than that 37% Faraday efficiency that I talked about in the very beginning? And this is really engaged a pretty broad team, and we've been looking at all of these different components over the last little while. I obviously don't have time to go through all of that today, but just to give you a glimpse into how we've been approaching the problem. For example, we've gone through and used 3D printing to test different flow cell channel geometries to figure out which one gives us the highest performance. And in the chemistry that we're using right now, we're finding the interdigitated version is the one that actually gives us a pretty substantial improvement over the serpentine and parallel style of flow plates. We've also spent a lot of time looking at different gas diffusion layers. And for those of you that work in this area, you know that this is actually pretty challenging. There's a lot of different components to go out and test. It's a lot of work to go and assemble all of these. It's a lot of work actually to assemble them and to get reproducible results, because there's very much an art form associated with generating these, just because there's just so many components associated with it. But for example, one of the things that we found is that using a microporous layer really provided us with a really substantial improvement in the performance of our flow cell. And so this is just an example of some of the things that we have found along the way. But again, these composite electrodes, I find there's so many components. It's really tough to do systematic studies when the level of reproducibility tends to be an issue, and there are so many components. And so one of the findings that I really like is this one that was made by Bill, who just got away from using these composite carbon electrodes and instead started using porous silver electrodes. And using these porous silver electrodes, he was able to drive up the performance of our flow cell from that 37% to over 70%. Actually, it's now over 90%. We've also gotten a lot better with our composite GDEs. So our composite GDEs as a benchmark, that is now over 70% as well. But these metallic foams are just so much easier to work with, so much more reproducible. And I think if you wanted to talk to any of my students about this, they would strongly recommend that you stick with the metallic foams. There's just a lot easier to build up the flow cells. Okay, so we had this system. We're now getting higher selectivities. We're starting to operate at higher current densities. But the one challenge we had was that we still had a system that was operating at pretty high voltages. Okay, so we needed to reduce this. And so just to demonstrate the issue that we have is, and I haven't really talked about it yet, is that because we're using this bipolar membrane to separate our anode and cathode, it turns out to be a pretty substantial voltage penalty associated with that. And in our system, you can see that even at low current densities, like we've got a voltage here that's well over 3 volts. And as we start to operate at higher current densities, you can see that the voltage just starts to spike. You can't even get up to 1 amp per square centimeter. So this was something that we really wanted to spend a bit of time on. Let's get this voltage down. Voltage really does matter. We reported this with Danielle a couple of years ago. Like, voltage matters. I know not a lot of people actually report the full cell voltage of their CO2 electrolyzer. If they did, they would probably find that many of these systems that are published end up with voltages that are, really too high to be meaningful. So voltage matters, and we've designed an analytical flow cell that allows you to measure the voltage in the system, and I encourage people to look at that paper if they're interested in learning more about that. Okay, so what are the sources of the voltage losses in the cell, and what are the sources of just the necessary voltages in the cell? So if we just look at the thermodynamic potentials of our full cell, for the system that I've just been talking about with our silver and nickel electrodes managing CO2RR and OER respectively, plus the bipolar membrane, well, that full cell voltage is minus 1.93 volts. Okay, so the CO2RR reaction, that thermodynamic limit is minus 0.7 volts. OER at the pH that we're operating at, that's 0.4 volts. And then we have a bipolar membrane that leaves us with a thermodynamic limit of 0.83 volts. Okay, and so these are the voltages that we needed to address. So we obviously can't make many changes to the cathode at this stage. But let's take a look at the anode. And we've been looking at this for several years, different reactions that we can perform at the anode just to get away from the oxygen evolution reaction. No one likes it. We make all of this oxygen. It's got a high voltage. It's got a high overpotential because it's a 4-electron, 4-proton process. And you spend all of this energy on making oxygen at the anode, and then you just simply release all of that gaseous product to the atmosphere. It's really, really frustrating. So we decided that, well, let's try the hydrogen oxidation reaction, the HOR, at the anode. And by doing that, we then would be able to lower the voltage of our system by 400 millivolts just by moving towards that different reaction. If we look at the membrane, as I spoke about before, you're dealing with a bipolar membrane. So that means you're starting with a voltage penalty of 0.83 volts. But actually, as you start to turn on your electrolyzer and you start to operate at higher current densities, the commercially available bipolar membrane that we have follows this relatively linear behavior here. And so that means that you can see that at 150 milliamps per square centimeter, we're already at 3 volts. And that's just for the membrane, okay? And we still need some room for the anode and cathode. And so for this reason, we decided to actually replace the bipolar membrane with naphthalene so we could simply bypass that 0.83 volts. And by moving to the HOR reaction, we could also make that possible for us. And so the punchline on this is that by working with HOR at the anode and naphthalene as the membrane separating our anode and cathode, we were able to reduce the voltage by a massive amount. And now we have a system that's capable of operating at 500 milliamps per square centimeter at slightly over 2 volts. All right, this is strikingly better than anything else that was out there in the literature at the time that we reported this. It's a fast-moving field, and this record probably won't stand for very long, but there were not any clear examples of systems operating below 3 volts at the time of publication of this. So we're pretty excited by these results. Now, the one challenge with the system that we really don't like, of course, is the fact that we're now feeding our anode with hydrogen instead of water. Okay, so there's a number of reasons why I don't like this. But if you, before you start to dismiss it as being an unreasonable reaction, we've done a techno-economic analysis on this, and we figured out that actually we could produce CO below the current market price as long as the hydrogen that we feed our electrolyzer with, as long as we're paying less than $2.30 a kilogram for it. Okay, now at $2.30 a kilogram for it, that's probably too inexpensive for electrolytically generated hydrogen. However, there are industrial processes out there where hydrogen gas is actually just flared from a plant. And so I can think of some pretty significant industrial processes where we might be able to make this particular system work and build a very strong business case around it. And so this is why we continue to look at this. I don't want to rule it out. The use of hydrogen on a global scale at the anode is probably not going to happen, but it would be, there are some niche markets where we could really make this work. Anyway, but we do want to try to find other anodic reactions, and we continue to work with that. The final point, the CO2 utilization of the bicarbonate electrolyzer. So recall that for a CO2, gas-fed CO2 electrolyzer, where 80% of that incoming CO2 goes out the other side. Okay, you're only actually using 20% of those products. That is not a very impressive number. We got to get better with that. How about our bicarbonate electrolyzer? Liquid feedstock versus the gaseous CO2 feedstock, pretty much the same flow cell. Check it out. We've got CO2 utilization rates that are over 2-fold higher than that of an electrolyzer using gaseous CO2. So we think this is a pretty big deal. Again, we're designing now a liquid-fed electrolyzer, easier to design and engineer, and it's got higher CO2 utilization rates. So to conclude, I currently contend that bicarbonate electrolyzers will save the world. I'm obviously being a bit facetious about that. It's still early days, and these electrolyzers have a lot of work that's needed before they can become commercially viable. And there may be something along the way that makes me realize that, in fact, this was not the right technology to go after. But again, if we look at these Sankey diagrams of taking CO2 captured from the atmosphere, going through the conventional methods of CO2 capture, desorption, and compression into a CO2 electrolyzer, and you compare that to our proposal in which you actually can use these bicarbonate solutions and pass them into an electrolyzer, and then take the output of that electrolyzer to go back and capture more CO2. And with the higher CO2 utilization rates, we're actually looking pretty good in terms of an energy analysis. And again, we've knocked out so much from a capital expenditure perspective. So I think there's something really interesting here for us to go after. And I definitely welcome more people to have discussions with us and really poke holes in our thinking around this. We'd really like to get more people thinking about whether this is, whether this has the potential that we currently think it does. Okay, so I'll just pause here, and I'm happy to answer any questions. I just wanted to thank Bill, Eric, Tengfei, Danielle, Max, and the rest of the team for all of their hard work in building out these bicarbonate electrolyzers. I'd also like to thank our sponsors, particularly Total and NRCan and NRC for supporting this work, and everyone for their attention. It's a real pleasure to be involved with this conference. Thank you.